Go for it.
All right. Hello and welcome to GLOBEBUSTERS Season 14, Episode 5. Today, Stone is going to take us through a little tutorial of Newtonian dynamics as applied to the solar system regarding the moon, and I think a couple other things as well. But before we get to that, we'll go ahead and introduce everyone on the panel. Shane G, how are you, sir?
What's up, everyone? Good to see everyone back again. We're going to have a nice, excellent presentation today, I think.
G, how are you, sir?
What's up, everyone? Good to see everyone back again. We're going to have a nice, excellent presentation today, I think. One of my favorites.
Have a nice, clean prezi.
Nice, clean.
And
no below the belt. No.
Nice.
Indeed.
Cami, welcome. Looks gorgeous out there where you're at in North Carolina.
Why, thank you. It's really nice to be here. I was touring in the backyard before y'all jumped in. I could, it's hot here. It is really hot here. And y'all saw me before the walk outside down the giant hill. I am now covered with sweat. So welcome. I think I'll turn the back camera on. Just
You moved 5 feet and now you're covered in sweat. Classic East Coast.
Oh, honey, no. Oh, that was not 5 feet. We went down the hill.
Yeah. Just any immediate movement, though, will ensue sweating. So let's see.
Well, we have the humidity that you don't need to even move here to sweat. You just don't need to do a thing.
Just blink. All right. Shane, how are we on the OBS connection? Are we good?
I think we're good for now. It disconnected immediately, but I think on the stream we just got like a 2-second gap, so we'll keep an eye on it.
Still live on the channel there?
Yep.
We're good? Okay. All right. Well, Stone G, whenever you're ready, good sir, bring us in.
Well, all right then. This, for those who are not sure about what's about to happen, this is a review of 2 videos that I produced and put out on BitChute. One of them a couple of years ago, one of them a number of months ago, sort of a part 2. And my typical format has to do with a couple of thoughts. I like to make my videos very short, very concise, very to the point, graphically rich, you might say, and you're going to see some of that here. But this all has to do with my thoughts about the moon. So you guys can see that, I assume. And then my mouse going around the mouse. Around
yes,
the moon
sir.
there. You can see. Okay, good. Then we will just bring up the notes and get on it. I just told you that my typical method of production, or the style of production that I have for videos, has to do with my thoughts about any particular subject, this one being the moon. But my modus operandi is something I also want to point out from the beginning for those who aren't already aware. And it's about the difficulties that I have with the issues I take with the globy assumptions being made about reality, and on top of that, the globy assertions about reality and the resultant globy formulae, which they use to pretend to represent reality. And this is all the stuff that we were taught in school, some in high school, some we paid for afterwards in university or college. And the more I look in to those assumptions, assertions, formulae, the more I see lies. The more I see these people have not thought this through, the more I see it can't possibly be, according to their own assertions, their own assumptions, and their own formulae. So this is what we're going to be doing, precisely that. And let's start with NASA, because we're talking about the moon. They are the privileged few who claim to have been there, not only have data about the rest of the solar system that we don't have, mostly even as amateur astronomers. They have some divine connection to reality, and they love to show it. Here it is when they show it. This on page 2, we're looking at something that is right off of the NASA website. It's called a planetary facts sheet. I find that a conspicuous title, but let's go with it.
These are the facts.
These are the facts. These are the quantified facts, which is really what turns me on. We're talking about the mass, diameter, density, gravity, etc., of these bodies we see going by in the sky. They're saying what they're made of. They're saying what their, gravity density are. They're knocking it out of the park. Here we are at 9.8 meters per second, for example. And
well, I think they even tell you how much what it smells like on the planet too.
So
doesn't it?
the little G on
it's just
Mercury
about.
is only 3.7 meters per second.
Yeah,
Oh, I
and the
see.
moon is
Okay.
only 1.6, which is 1/6 of 9.8, right? This is where they begin to spin. And this is one where you find when you look into all these variables and all of these figures for all of these bodies, the more and more you look into the interrelation of them and check it out, for example, to scale, which is something NASA never shows you, something in the textbook you never see, it becomes all the more bewildering just how they can confidently assert any of this. Let's just put it that way. So front to back, these are the physical characteristics of the solar system that they describe. But it leaves me with the question, when I look at this in terms of real figure, what's holding the solar system together? What is keeping all of these things in orbit around each other, around the sun, on the same ecliptic, et cetera, et cetera? What is that? And of course, the answer is the big G. This is their God. This is their ruling force. This is the thing they can never seem to isolate in experiment. And that formula right in the middle there, that's courtesy of Newton. For those of you who don't know, this is a force, and we measure that in newtons, ironically enough. This here is the gravitational constant. We frequently see that on sufficiently sophisticated calculators in the form of 6.67 times 10 to the negative 11 as far as the value goes. Let's not talk about the unit because it can get pretty clumsy and crazy in how you express it, in whether you're talking about grams and dynes or whether you're talking about kilograms and meters, et cetera, et cetera. The mass of one body, the mass of the other body, and the distance between them. Now notice, this is one crucial point, that there's only one exponent here in this formula, and it has to do with the radius. It's the entire denominator of this fraction, and it is squared, as in the farther you go away from it, it drops by its own intensity squared, as in you go twice as far, it is half as strong, 4 times as far, 1/16 of the strength. Hope that makes numerical sense. But that is the interrelation that I want you guys to keep in mind as we blow through the rest of this. And all of it, of course, rests on this assertion right here, which, they assert that people like, what was it, Eddington or Cavendish, I can't remember which, I think it was Cavendish, asserted that this is what's going on, and he did it in his garage.
Just a man in a shed can accomplish many things, such as weighing the Earth and the sun.
If you look at your instruments through a telescope, it must mean you're not affecting them. So that's the assertion that the globies are laying down here. And the question is it true? Is it? Let's take them at their word for a sec, and let's deal with this formula, of course, starting, forget G, we'll just leave that as a understanding that that's an extremely small coefficient. It is a very small number, 10 to the negative 11. This one is going to be the mass of the first object and the mass of the second object. And in the case of the analysis here, we're talking about 3 objects, the interrelation of these forces between 3 objects, the sun, the Earth, and the moon. Okay, that's all we're juggling here. Think of it as a 3-body problem if you like, but we're going to isolate these things as much as we can. So this is dealing with the mass. There isn't a lot to digest here, really, only the interrelation that this is the alleged mass of the Earth with 22, or rather an additional 20 zeros beyond what you see. And this is what we're represented with in integer notation: 3, 6, 9, 12, 15, 18, 20 zeros, and 2 more for the decimal point. gives
No.
you this exponent right here.
That might be the purpose
Okay.
of scientific notation, to hide the lunacy of such ridiculously huge numbers. Isn't that the whole
It is
point?
precisely the purpose of scientific notation, which is why they gave it the term scientific notation. Ho, ho, ho. Like, why don't you just wrap it in a white lab coat, if you know what I'm saying? The interrelation between these, of course, is that between the Earth and the Moon, like we were seeing that 9.8 meters per second squared versus 1.6 meters per second squared we were looking at on the planetary fact sheet, that is because allegedly the Earth is 81 times the mass of the Moon. And in turn, the sun is 330 plus thousand times the mass of the Earth. These are the figures that NASA give us. So we're going to go with them. That's about as far as I can take this part of the concept. Hope that's all firm in everybody's mind. Just about how many zeros are involved. Speaking of zeros, here's a few more when we're dealing with radii. Okay, this is the distance from here to the moon. On average, they say 384,000 kilometers. That's what we're looking at there. If you take that over to the 6, it's a millions of meters, and you break that in half for thousands, and that's what you get. 388 times as far away is the sun from the Earth. Isn't that wonderful? So we're here at 384,000 kilometers and 149 million kilometers away. Again, huge numbers, but what we're going to do eventually is we're going to chop all these down and show you how the harder parts of the figures interrelate. Let's see, do I have anything else on 5? Yeah. Think of it this way in terms of the fraction of the distances between them. I mean, it's fine to see 388, but what does that really mean, one to the other? Put in your mind that this 384,000 is around 1/4 of 1% of this distance. Maybe that'll stick a little harder in your own abstract sense of what's going on. And this is what NASA shows us in regard, at least to the first two bodies. A nice, pretty round thing. This is actually one frame of a video put out by NASA where the Earth is spinning in the video, you know, doing the 24-hour thing. And the moon is spinning around here doing the 28 and a bit day thing. And this little arrow here represents the amount that the moon just also happens to spin, so that the same face of the moon always faces the Earth as it goes around and around and around and around and around for millions of times in a row, with no other forces acting on it because it's in a vacuum and it's flying through space, right? Somehow this rate of rotation exactly matches this rate of rotation.
I have a question.
Isn't
I have a
that
question.
amazing? What's up, Cami?
Wouldn't being hit by a meteor knock it out of orbit?
Do
sorry,
you
I'm
would
just playing
think
school-
that all
I'm sorry,
of
I'm
the
just playing
bodies could,
schoolhouse.
there you go, man. Exactly right. That if we were looking at real physics flying through space in a vacuum, that a piece of rock would come by here, tangentially hit this moon on this side or that side of center, and change its rotational value. You would think that would happen, but no. They use a new expression, or a novel expression. They say that the moon is, quote, tidally locked on the face of the Earth. Like somehow that it's not homogeneous in terms of its, or homogeneous rather, in terms of its density, that some denser part of the moon is on this side underneath the surface of the moon, and that's what pulls it towards the Earth, that gets this rotational thing going. Yeah, okay.
The classic tidal lock.
Why didn't that happen with the formation of the Earth with the sun? It goes around with absolutely steady rate all the time, or as we blow up this way, you know what I mean? In this case, you can see, I should say, as we blow this way in orbit around the sun, because currently the sun is in this direction, off the 5 o'clock direction in this image. You can see by what's lit that as we're doing that, why wasn't the Earth's rate of rotation changing, going up and down daily due to differences in density threw it as a ball as it formed in a vacuum in space through lateral accretion, just like every other body we allegedly see in the sky. Another cool thing to think about. And scale is another thing that I would take them to task on regarding this cute little animation. Forget this perfectly circular orbit. They claim that the moon is actually 43, 46 Earth radii away. So it is far off the page at this scale. It's just not even close. And finally, where is the sun in relation to that scale that I'm just pointing out? This is really the crux of do you believe it or do you not, and why? Do you believe it or do you not believe it? Okay, so let's take a peek at the orbit itself, and here it is. And so here's where we start to get into significant figure. This distance between requires, if it's done to scale, that the Earth be this small and the moon be that small. It's not just a blemish next to the arrow. Let me bring it over for you. You can see this teeny little gray splotch. That's the moon in scale to an Earth this size at 384,000 kilometers away. Okay, so you can see that the actual path of the moon in the middle between these two lines, this is the average radius at 384,400. So there is a minimum and a maximum on either side of that value, such that the difference between them, the minimum and the maximum, is about 11% of the total average. You see that in this image, the sun is off to the right, that the moon is allegedly pulled towards the sun, maximum distance from the Earth over here somewhere, and then here closest to the Earth because it is being pulled allegedly by both. Hopefully that makes some sense. So
Yes.
what we're going to do is we're going to zoom out a little bit. We're going to get out about 50%. We're going to get about twice as far away, and it starts to look like this. Here's our first 1,000,000 kilometers away from Earth, and this is roughly the 400,000 mark. So you can see that it falls about there on the meter. There's your 384, and the sun, like I was saying, is 388 of those to the right in this image. So how do you put that on there? You don't. And this is why NASA never shows us anything to scale, because if they ever did, they'd show us exactly how ridiculous the scenario is in terms of real figure and real, to scale graphic. Again, here's the rough size comparison when we're looking at the Earth being this small that you could barely see it. The moon, forget about it. It's a memory in terms of being able to see it. This is about 1.4 million kilometers in diameter. Here we are showing it 9 million kilometers away from the Earth, but it isn't 9 million kilometers away according to the Globies. It's 149 million kilometers away according to the Globies. So what does that look like? Well, you remember that the moon is barely a thought here anymore in regard to size. And the Earth, you can barely see the green splotch there, like a pixel perhaps. Well, when we break it down to 149, that's what we're looking at here. And I have to actually zoom out just to get the sun into the picture there. Can you see him on the far right? That little teeny guy. So here's 0 just at the edge, and Earth and the whole circle there, it's a blemish. You can't even really see it at all. And here we are 149 million kilometers away at still 1.4 million kilometers wide.
Just in terms of putting this to scale, I think thinking about how they argue tides and tidal lunar acceleration, they're saying that there's solar and lunar tides. So the moon is pulling tides from all the way over there, and actually from that tiny little yellow dot way on the right is actually also pulling tides in the opposite direction of the moon. That's the actual argument. That's insane. Okay, thank you.
Yep. Oh, it gets loonier than that, but no, good, well put, I should say. Yeah, somehow the moon swinging around the other side is having about the same influence as the sun being way the gomp over here.
2.31 stronger, right? So the moon is 2.31 stronger times than the sun.
Don't blow the punchline, Shane.
Okay.
Oh no! That's the whole point of part 1, which is what we're looking at here. But yeah, so there we are at 149 million away. And
It's
they
nice
want
to
us
see
to
it to
believe.
scale. You often don't see it that way.
Yeah, like
you never do. You never
just
do.
seeing it like that makes it look ridiculous from every side. It's like, oh, that other thing I was talking about, that's also ridiculous. I didn't quite get that until right now.
Right. I've never seen this in a textbook. I've never seen this in a NASA diagram to scale. Not anywhere. I challenge somebody to find it and post it. That would be great to see, because they would be finally telling the truth about something they talk about in terms of their own assertions. Wouldn't that be great? Okay, so again, this is where we're going to go back to the formulae, and we're going to use those Globie assertions about precisely what you're seeing here. In this, they're trying to assert that there's some kind of gravitational attraction between these, and R dropping off per square. Do you know what I'm saying? Like how ridiculous that assertion is when you look at it in terms of real figure. That's where we're headed. So it's a lot of numbers. Don't worry about that. Just follow the bouncing ball, and we're going to find a way to put this into coherent terms. So here we are with the formulae, and we'll zoom out just a little bit, just for the sake of seeing the whole rectangle.
Got to get a scale for just the formulae.
Yeah, you got to back way out. Get your wide angle lens out. And again, this is the formulae courtesy of Newton. And there's G broken down for you in terms of the value. And we don't really care about the unit. We just care about the end value, the total. So when we talk about the force of attraction between the Earth and the Moon, we're taking G, we're taking M, we're taking M, we're taking R squared, and we're coming up with this 19810 to the 20th. And this is the integer value of that right there. Okay, 18 zeros on top of 198. Yeah. Is that enough? Hell no. Sun, moon. Here we are with G. Again, the M, the R squared right there. And that's 436, 10 to the 20. And that's right underneath. Again, the sun pulling on the Earth. Many times that. Same formulae, same drop the masses in. Here's your radius. And you come up with this to the 22nd exponent. So again, mind-bogglingly huge numbers that the brain simply cannot break down and interrelate. That's on purpose, gang.
Can you tell us what that number is? Can you give us the
feel free to use the word bajillion.
35 quintillion, dude.
Yeah, these could be octillions by there. I mean, this is there's million, billion, trillion, quadrillion, quintillion, sextillion, roughly the sextillion area.
What I can tell you that how if you spelled out your numbers, you know, ONE, TW, how high would you have to count spelling them before you got through the alphabet?
I'm not sure I understand the question.
9/11.
So it would be like, for instance, we'll give you a clue to like how wild it is. Until you get to the number 1000, you do not get to the letter A. If you think about it, 1000 would be the first time you come across the letter A. So until you do that, 1, 2, 3, 4, 5, you will not see the letter A until you get to 1000. You will not see.
Even in this first number, Cami, you're not going to see A, because this is 198 and you've only got 26 letters. You're not going to see it until you hit, what is that, 4, what is this, sextillion, 4 sextillion, and then you finally see A.
Right. With the way they, after a while in the counting, after a while when you count, you just start adding illions onto the end of them, adding another illion on. And so the numbering gets really repetitive. So you actually never get it through the whole alphabet, and you never do use the letter J or K. So bajillion is not, what I can tell you is, by knowing that fun fact, bajillion is not a real number.
It's one of my favorites.
No, I think we're looking at almost a zillion, jillion right now.
You are looking at,
it's 35 bazillion, 500 bajillion, zillion.
Unreal.
Well, there's definitely a point where you can just make it up.
Illion. It starts where you just keep on going illion.
Let's make further effort to declutter what's going on here. The G I've always left as just plain old G and left the number here, right? So what we want to do is get rid of a whole bunch more numbers and a whole bunch more zeros.
A whole bunch more.
So that you can see how they numerically interrelate. This is what's most important. So here's another step. This is step 2, where we're getting rid of all the zeros here in a sec, but we're assigning letters to the values. that the value of the attractional pull between the Earth and the Moon will be X. Between the Sun and the Moon will be Y. Between the Sun and the Earth will be Z. Okay. And then our next step, of course, is to get rid of all those zeros. Arithmetically speaking, these three numbers interrelate mathematically the same way that these numbers interrelate in terms of ratio. That you multiply this one by 2 and some, and you get that one. Whatever it is, 81 times to get that one. Well, it's the same is true with these numbers right here. They are roughly the same. It's just that all we did was move the decimal place. Hope that makes arithmetic sense for everybody. That's where we're at. Okay, so when we got our letters and gears, well, you don't cancel them out. You just kind of algebraically take them off to the side.
Right.
Yeah,
Just
so
put them
it's
aside
ratio
for a
and
minute
proportion.
for visuals. Yeah.
Mm-hmm. Just so that the mind can wrap around the figure. You can't play with that.
No, I can only see in 35 sextillions, bro. These little tiny numbers aren't cutting it for me.
Yeah,
I
just
can't even
see the resolution between hundreds. No. So yeah, here we are with those. All right, well, let's take those and apply them back to NASA's favorite picture. That these are the forces of attraction between the bodies. X between the Moon and the Earth, Y between the Sun and the Moon, Z between the Sun and the Earth. And this is where we find out why we did all of this exercise at all. What was all this for? It was to identify this figure X and this figure Y and try to come to terms with this beautiful circle. And how can that be is the question. How can that be? How can we have only a 13% ellipticity here, and at the same time, this is pulling on the Moon twice as hard as the Earth ever does? You know what I mean? That's the question. What were you going to say, Alan?
I'm starting to think these numbers aren't going to lead us to confirming heliocentric dynamics.
I think you're definitely catching a whiff.
Starting to make me nervous.
No, we're forget starting. We're done with part 1 here, gang. This was the whole purpose of a whopping 3.5 minute long video that so few people have even come to watch yet. I'm amazed that I'm not getting the views that I think I should here. It's mind-boggling. But anyways, what this works out in terms of ratio is that this Y is 2.2 times this X. That the force of attraction between the Sun and the Moon is more than double, comfortably more than double, the alleged force of attraction between the Earth and the Moon. How can that be when we observe 13% ellipticity between closest and farthest away from the Earth? And it comes back to the same exact spot every month. Every month, it just completely ignores this ratio. How can that be?
Just the most symmetrical tug of war ever.
That is how, ladies and gentlemen. There is only one conclusion there. In a very glib way, I thought that by the end of part 1 here, which it turned out to be part 1, but by the end of this video, which I thought was fairly definitive in its assertion, that there really wasn't much left to talk about with regard to Newton and the solar system and frankly Kepler.
Wait, are you saying that the Sun exerts 2.2 times stronger a force than the Moon?
Than the Earth.
Oh.
On the Moon.
Okay.
Yes.
All right.
Yes.
Because they go the other way for tides, right? They're like the Moon exerts 2.2 times a stronger force than the Sun.
Oh, because it's so much closer, you know.
Yeah, so using the inverse proportionality of distance, they found the distance metric that would make that mathematically true, but in reality, it looks ridiculous.
And they ignored Newton altogether.
It looks ridiculous.
They just created a new formula, did a little mathematical work in front of you, hussa, putza, and you have a new conclusion in the textbook. And all the little students ate it, just gobbled it up and regurgitated it all over the exams. They got their sheepskin, that they paid good money for, myself included, and walked home with a big smile on their faces, feeling ultimately qualified to tell people how it is. I was shocked to find that the globies were not satisfied
They
with any of
demanded
this.
more.
No, I got all kinds of reactions. I'm sure you can can guess, not very positive reactions. And of course, I mean, is it ever over for the globies? They will never accept defeat. In fact, what they retreated to on this one was the assertion that there's just not enough math on the page. That I don't know how to
needs
do math.
more math. Oh,
You got it.
no.
Not enough math. There are some other forces you forgot about, bro. So because you forgot about those other forces, you must not know anything about math. Therefore, everything you say is incorrect. Therefore, this video has been debunked. You know,
What other forces?
I'm so glad you asked.
Jesuit mysticism.
I am
PSM.
so glad you asked, because that is precisely what we're about to handle. So let me just do a little document shuffling here just for a sec before I reshare.
Yeah, when people say Stone doesn't do enough math, he shows you free body diagrams of it. He's like, oh, you would like more? You want to see every possible like the force of magnitude for every vector? Okay.
Yeah.
Looking at you.
But the globular retort to this is simply you didn't do the math right. Even though we just went through it.
Yeah.
That's always their answer. It's never that they're wrong.
Is.
Yeah. It's like you didn't do it
That
right.
actually is the response that I
All
got.
day.
Is like, you don't know nothing about math. Why are we listening to you at all, et cetera, et cetera, et cetera, et cetera. Oh,
So I think the big refutation to what you put forward was Stone forgot to account for the centrifugal force or something. So I think they were saying that the rotation of the moon offsets the whole thing. It's just like that's what makes it.
Well,
that's what makes it work.
Permanent equilibrium is part of the gig, as they say.
Crazy, dude.
They wanted to pretend to confound me somehow, saying that frankly, it's not even the moon's orbit around the Earth, which is the determiner here. It is his actual movement around the sun with the Earth, that net outward centrifugal force.
Right.
So that's the one they were challenging me to compute, like, because I don't know anything about math, right? And so
I thought you compensated for that. I really thought you compensated for that when you put in your equations
in
for
part
the fidget
one.
Spinners. Yeah.
Oh no, they're
on the fidget spinner where you compensated for the fidget spinner effect.
I'll have to work that into part 3, I guess. We get the fidget spinner coefficient, put it in there. See if the math still works out.
Well, today in the news, it's because of the reservoir in China that they're building that's going to put us.
Right.
That was
we slowed it down by a femtosecond or some jack figure.
We did.
Dude,
we're going to know
that's
2
so
seconds. We're
funny.
going to know. Do you know what? In 500,000 years, we were going to know that 2 seconds were gone.
And life will end. Yes, that's for sure.
Didn't they use that story before on another dam that was built like in South America or something? I feel like I've heard that
They've
before,
done it on
years ago.
Just play the hit.
Every time something gets built, they're like, it's gonna change the Earth turn.
Just,
like, okay.
Just play the hits, man. They don't care which dam it is. As long as it's another headline, it's some more clickbait. Everybody's happy. Rent's paid. We're good to go. You know what I'm saying?
Excuse me.
No problem. So this, of course, necessitated a part 2, where frankly, all I can say is I love it when the globies double down. And they just think, no. And I say, So here we are in the middle of the second about the moon. In part 1, we were looking at, like you said, we were only looking at the centripetal attraction and the 13% eccentricity, that ellipticity of movement around the Earth, and that it's pretty close to circular given the 2.2 ratio problem. Okay, so this time I started off with something I heard Pizzo talking to another hopeless globie on a Friday night on X. And I featured some of this discussion because this is actually the underneath what you hear before I drew all over it is an image that Pizzo produced in order to argue with this globie. And you can see his main question is just like mine in red in the lower center. Why does the moon continue to move back towards the Earth when we've got this outrageous force acting on it from so far away? And he came to the figure of 2.19. I'm fine. 219, 22. It doesn't change the argument at all. I'm good with that. His little circle here is circling the two values that we were floating around with in part 1. This 438 and the 2, both of them to the 20th exponent. Newtons as an attractive force. Okay, well, great. But now it's about 4 vectors, and it's which 4 is the question. And that's what this diagram here is all about. It's the centripetal, just like we were talking about before, the force of attraction, this red and this red, both the sun attracting the moon and the sun attracting the Earth, using Newton right down here. And then we use a little bit of Kepler up top for the centrifugal ones, the 2 blue arrows, where it's this orbit net as this line actually goes way out to here and then way back to here for the next new moon. In between, right here where you see them, this is the new moon position where you don't see the moon at all. All you see is the sun in the sky. A whole other separate topic. But anyways, those are the 2 centrifugal ones where we're using the mass of the thing flying around times its velocity squared over its radius. Again, here we're over its radius squared, and here we're just over its radius. That's page 2, and them's the notes. So them's the 4 that we're looking to establish. Where did I get my data this time? Well, not NASA. This time we went to timeanddate.com because I see Globies referring to their data constantly. So I figured, well, that's where I should start. Makes sense to me, hey? As far as the timing goes, this is all the data for September 2024. This is the month where I began to produce part 2. And when we zoom right on in, what we're looking at is the date and then the times for when they come up and below our visual horizon. This is the meridian passing. This is when essentially lunar noon occurs for you on your point on the Earth. So on, where is that 1306 value? That is on the 3rd of September at 1:06 p.m., 48.8 degrees off the horizon, looking upward. That's where the moon is at precisely 1:06. Now, 24 hours and 39 minutes later, it happens again, but the moon is a little higher off the horizon. These are the distances we'll be using. This is the alleged distance of the moon from the Earth as it goes by day to day. And what else have I got here for notes for page 4? Only, you should take a look that we're actually right down to the kilometer, right down to the 1,000 meters. Does anybody find that suspicious at all?
Got it right down to the millimeter.
Like we're talking about one. Let's see. Let's get this right. 1/4 of 1,000th of 1% of the total distance. Okay, that is the level of precision that NASA is asserting and timeanddate.com are asserting in this figure. Again, 1/4 of 1,000th of 1% of the total distance. That's their level of precision. And it's sillier than that. Wait till we get to the end of this. Just before the absolute hilarity, total punchline of this scenario here, I'm going to come back to that. So be ready. Like spit your coffee everywhere.
Dude, they got the exact distance. It's hilarious.
It occurs to me that's what happens when you try to quantify mathematical ratios empirically, right? Like if it's really just a ratio, say with Kepler, or as we're looking with the celestial theodolite, if you just arctan a tangent, you're gonna get the same answer every time. It seems to be something similar happening here.
Yeah, well, the same way that you have people in your arena arguing things with arc-second precision. using a plumb bob dropping 3 feet underneath an instrument. You know what I mean? That kind of thing. I find typically that the higher level of precision claimed by a Globie, the worse the situation they find themselves in by the end of the exercise. You know what I'm saying? Okay, so the data here is this is the new moon, which took place roughly on the 1st or 2nd of September over here, right? By then, we started the clock at the new moon. 24 hours and 40 minutes later, it came around again. 24 hours and 39 minutes later, it came around again and hit us right at lunar due south noon. Highest peak in the sky. Again, 24 hours, 39 minutes later. This is the sum day by day by day by day of these figures here. So you just add this, put it in, add this, put it in, add this, put it in, etc. All the way down. 720 hours later, it's a new moon again. Okay, and these are the alleged distances from the Earth that the moon was, say at full moon. Here we are at 357,000 kilometers away. That's kind of where we're at with the figure. All right, so let's see, page 4. Let's give her to page 5 and have some more fun here. This is where we take things a couple steps farther in terms of graphical analysis of the exact same figures we were just showing you. So there's 5 and there's 6. Yes, two-dimensional representation. Here we're coming up to the 400,000 kilometers away. The blue line and the 2 pink lines are from part 1. This is the 13% eccentricity, ellipticity of the path of the moon, which is the yellow, or rather the light blue line here. Closest point. Oh, and in this diagram, the sun is on the left, pulling the moon to here at the time of a new moon, pulling it close to the Earth at the time of the full moon over here. Now, notice the asymmetry. This is, again, a little bit tertiary to the analysis, but just something I wanted to show. NASA, again, shows nice, beautiful, perfect circles. Well, even if we just take these movements, which they are fairly nice and even and stuff, what about when they happen relative to sun angle and proximity? Notice that this is when the new moon happens, that there's, directly opposite, or conjunct, I should say, conjunct with the sun from our perspective in the middle here. But here is the point at which 2.5 days later, the moon is actually at its farthest point away from the Earth. How do they figure that out? All they're talking about there is looking up at the sky and how does its angular dimension change? How does it actually, how big in the sky does it actually look on that day? This is the only value that they're using, other than the other presuppositional, assumptions that pour out of Kepler's formulae, et cetera, for calculating floating bodies in vacuum. Somehow, after the new moon, after its closest point to the sun, here, 2.5 days later, it is finally the farthest away from Earth. But conversely, over here, when the moon is on the other side, allegedly being pulled by both, gravitationally speaking, a couple of hours after totally full, it is at its closest point. Not symmetrical at all. It's not something you can gather just by looking at this cute blue line and how it falls within the pinks. You know what I mean? That there is an asymmetry. There is a bit of an oblong nature to this path that, come on, guys. Are you catching a whiff? Are you getting some of this? Okay. And while all this is going on, the sun, or the Earth rather, is here. We are seeing it, looking down from the top, so to speak, sun way off to the left, and it's blowing by the screen here at 30,000 meters per second. It will go from here in terms of real space to this 400,000 kilometer mark every 3 hours and 40 minutes. And of course, the moon will be going with it, et cetera, et cetera. So our view in terms of the ratio will never change, just giving you a rough relation of orbital speed, Earth and moon to the sun, and orbital speed, moon to the Earth. Hope that's clear. Alrighty, page 7. This is where we start to take this delta y, which I'm plotting here. Delta Y being, are you ahead of the Earth in terms of your orbital speed going around the sun, or behind? A negative delta Y value, or actually a negative Y value. The delta is how it's changing over time. Okay, here are the Y's and how it's changing over time. Not its actual Y velocity, but its delta Y. We use that in combination with this 30 meters per second to produce a net speed of the moon going around the sun here. And you can see that it exceeds 30 kilometers per second and then gets below 30 kilometers per second based on its position. Here we're going faster. Here we're going slower because we're falling behind the Earth as it goes upward on the page. Hopefully that's clear.
So
in terms of the relation of how we got that number.
when they're saying the things in the sky are going faster and they're further, they're really just talking about its change in angular size as observed from Earth. Right? They're just extrapolating that must be it's further and distant, etc. But it's really just getting smaller and bigger slightly in the sky.
They did the same thing with the sun, precisely the same thing with the sun and its variation, etc. So what we showed there was the delta Y and how that's changing in terms of the moon speed around the sun, right? But the same thing is going with its radius in terms of its delta X, distance from the sun, larger, smaller, right? So that's producing this. And you can see that in terms of the total distance, there is only 0.5% variation, maximum to minimum, in this value. In turn, we see only a 1% variation in the centripetal attraction between the sun and the moon. This is the G that came from part 1. Okay, then what about the whole centrifugal thing, the flying outward from the Earth, the flying away from the sun, which we're handling in this set of figures here? Well, here we are. With its speed, that's the v squared in mv squared over r. This produces the outward force in newtons between the sun and the moon. That the moon is flying in orbit around the sun, that if we canceled all of the attraction, this is the force at which the centrifugal would push the moon away from the sun. It would fly off if there was no attraction over here, no G holding it in orbit. Hope that's clear. So to produce the pinks, it's really the difference. Here's the attraction. Here's the flying away, the centrifugal. This produces a net figure, a difference between them, G minus F. And all we did over here was, again, we took all the zeros away. We took 17 decimal points away to produce these figures, which are actually these figures shifted on the number line. All we did was move the decimal point. Why? So I can take these figures and give you a graphical representation of the difference between these two forces over time in a month as it goes around the Earth, as it continues to go around the sun. And then we did exactly the same thing with the Earth and the moon. Slightly different spread of variables, but these are the resultants that come out of it. That the speed of the moon around the Earth, which is essentially what is, they claim, causing that eccentricity, because it's going faster here and slower here, and it's closer and it's farther away as a result of this speed, and that there is a constant, perfectly balanced interchange between these two, such that the moon never changes. Each time it swings around through the sky, it's on the same freaking path, year after year after year after decade after century. Try to figure that out. Anyways, here we are with part 1, the attraction between the Earth and the moon. And here we are using the mv squared, again, producing a 12% variation in the centrifugal force, which would cause the moon to fly away from the Earth if this one allegedly was not around, holding it in orbit. Difference between the two, here's the set of big numbers here. Again, we took off 17 decimal points. to produce these numbers. Okay, 6 positive, 16 negative, 30 negative, back up to positive to the tune of 700 positive, which means that the force of attraction is far more than the centrifugal force pulling it away at this point in time. Hope that makes sense, because now we're going to show you the graphics and how those look. This pull to the sun are the pink numbers where we went from 277 down to about 10 and through 0 all the way to negative 320 and then cyclically back up again to 270, 280. And that's what you see here, 270, 280, all to 320, over to 280. So at the time of the new moon, the pull toward the sun is the greatest on the moon. And at the time of a full moon, when it's around the other side of the earth and farther away from the sun, and it's r squared, remember, it's net wanting to pull away from the sun. Okay, well then what about the moon and the earth? Here we are again with 6 going through 0 to 700 and then back down to roughly 0. And that's what's going on. Again, new moon to full moon to new moon. New moon, when it's much farther away from Earth, the pull is away from Earth. Here, where it's much closer to Earth, the pull is towards Earth because it's r squared, which is really the governing factor here. Hope that makes sense. Okay, so those are what they are. Here's what they look like when we start to add them up. We're literally taking those 4 vectors, and really we're dragging it down to a sum of 2 now, aren't we? We took 2 to produce this, 1 out and 1 in, and we took 2 to produce this, 1 out and 1 in. Now we have 2 values that we're going to add, and we're going to get a sum value out of that. And that would be the net force acting on the moon at any given moment. Now, these lines are a bit thin to see, but if you see how they are applied and in what order, it's a little more intuitive. This one time, the pink line is the opposite of the 2 pink lines I've been showing you up till now. This one is actually would be on the minimum line if I had drawn spherical lines to match these pinks, right? There would be 1 pink just inside all the way around at that distance, at that radius away. And then another one out here by the S, the second S, all the way around the outside to match where it is in terms of the moon. You see that the blue's on the inside here and the blue's on the outside over there. The pink one, X equal Y. The pink one is centered on the Earth. This is your average. This is your 384,000 right there. So here it's less and here it's closer to 400,000, like we saw in the first diagrams. All right, again, 2.5 days later, farthest point away. Hours later, closest point to the Earth. And I hope that all makes sense. Again, the sun off to the left. Okay. In terms of the lines that we're seeing, we actually did them the other way around. I started with the blue line coming in here. This blue line here represents this blue line right here at about 700 pixels long. In this particular, I take the same proportions and apply them to this. And I have this attraction in the blue line. The pink line, again, going all the way back here, is this line, pulling it away. Equivalent value for value, force for force. So we have the blue line coming in and the pink line away because it's swinging away and it's farther away from the sun, so it's much longer than the pull towards the sun here. Again, the blue lines over here are very small, that it's almost balanced. The pull between the Earth and the moon, so it's negligible over here, isn't it? Okay, so let's sum them up. Green arrows is what you're looking at. That again, the blue line to pull it in and the pink line pushing it out, net. This is the net force on the moon in this position on the blue line with the sun over there as the whole thing is blowing around the sun at 30,000 meters per second. Okay, well, here's what it looks like when you create a shape out of all of the nets. This is the direction of the net push-pull on the moon as it goes around the Earth, the whole thing flying around the sun at 30,000. Now, okay, what I point out in the video is really the punchline to this, that when we're talking about the moon's path here on the light blue line, and it's coming around this way, the vectors seem to make pictorial sense. They seem to make additive sense. That the green says, yes, you should be speeding up. Yes, should be getting closer to the Earth. Yes, 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 yes. And now pulling much closer to the Earth, but not really speeding up much. You know what I mean? There's a little bit of pull away, but the net of these forces is what we're looking at. That it's accelerating a little bit still, but there's a fair bit of pull, right? So as the moon travels this path, the green lines are suggesting it should be turning left, which we see that it is. It's turning left on its path because the green arrows are pulling it off to the left. Conversely, as we get to here, when it is on the blue line and it is continuing to turn left, just like it did over here, it's over there, continuing to turn to its left, all the way down here, while all of these arrows are saying, hey, buddy, turn right. The net force on the moon at this point, Earth versus sun, produces a pull towards the sun. However, the moon turns left, turns left, turns left, turns left, violates the formulae, violates the physics that we all studied in school, does the exact opposite of what Newton and Kepler predict it should do. Well, game over, guys. We came to exactly the same conclusion. Now, here's some more really weird, oh, how precise could they possibly be down at NASA? If you can read that, it says currently the moon is slowly drifting away from Earth at about 1 to 2 centimeters per year. Insert chuckle here.
Stone, I noticed when you added up all the vector quantities, it didn't make a perfect circle. That didn't,
Dude,
doesn't make me feel comfortable.
You know what I was thinking?
It didn't come close now, did it?
If
No.
like if you had to draw a 2D representation of a lumpy, misshapen geoid as a circle, I think that's what it would look like. That's all I'm saying.
Yeah, it does kind of have a squashed orange look about it, doesn't it? Like somebody threw it off the side of the road and there it is now. It used to be nice and round. Yeah. So this is the prescribed orbit of the moon around the sun as they both, or around the Earth rather, as they both go around the sun. All right. This is the prescribed orbit that the physics say this is the path the moon should take for September 2004, based on the distances we say things are away, based on the masses we say things are over time.
That's hilarious.
But it just doesn't.
Now,
It doesn't do
wouldn't
anything of the
that,
sort.
because the vectors don't, when it completes the circle, because they don't all go radially inward, doesn't that mean momentum isn't conserved when it changes directions like that?
It means momentum is completely violated.
Yeah.
It means that kinematics, everything we learned about kinematics is
Dude.
broken right here.
Okay.
Right
I was
there.
just watching something on parallel vector transformations, and the exact violation just struck me there. Yeah, because they're all supposed to go radially inward if they go
Yeah,
out,
they should all be like this.
That's a huge no-no.
They should all be like this. They should all be like this. Net.
Yep.
And frankly, they should all equal out to the blue. You know what I mean? There should all be equals out to the blue. The green lines should all point to here, to here, to here, to here.
The blue's the actual path. So you're saying the forces,
that's the actual path.
The forces should conclude and match the natural path, but it completely doesn't. Based on the direction and the force. That's amazing.
Right.
Yeah.
So picture another blancmange like this, downward and to the left even more. Every month in this direction, every month in this direction, every month in this direction. That's where the moon should be by the end of the year. But it ain't. It flies through the sky with absolutely mind-numbing identical precision year to year. It's in the same freaking spot.
They model it with perfect circles, and then they mathematically predict it with like 3% ellipticity, right? Is that what that blue represents?
13.
Oh, 13? Like just slightly off, perfectly circular. And then the actual path that would be dictated by the forces is this misshapen geoid thing, which is nothing like that. Okay.
Yeah. Yeah. And it violates kinematic law right there.
Yep.
Like
violate.
for nearly half of its travel, it's doing what physics said it shouldn't do.
Yeah, that's crazy.
Are we
That's
having
illegal.
fun yet?
It's illegal.
That's why I said, hey, forget it. That's not crazy. This is crazy here. This is Terrence. What's his name? Davis. Crazy right here, talking about how the Earth is moving away by another 500,000 years. It'll be out of the Goldilocks zone and yada yada, because it's moving away at 12 inches per year. Some jive figure, and they're doing the same thing with the moon right here. They're saying, oh yeah, we have an ability to measure with such precision something that is 384,000 kilometers away, that we can measure a 50th of a thousandth of a kilometer in terms of resolution for distance.
You're right. Calling
absolutely preposterous.
Calling into account the precision with which they were predicting does highlight the drasticness of how far they are off with the actual predictions.
Yes,
you are right.
I'm glad you can see that proportion. Okay, let's just make one final death blow to what's going on here regarding Newton. Keeping all of this in mind and everything we know about what a blunder this is, mathematically speaking now, that we've proofed all this out with real data from timeanddate.com, right? We took NASA planetary facts, we put them all together, and this is the sum. Keeping all that in mind, it all came from Newton, right? Well, here's Wikipedia's entry about Newton talking about this orbit. That he developed a theory of motion. Well, I'm glad they're still calling it a theory. Newtonian mechanics. What an awesome title. But the point is that the observation of lunar motion were the main test. This is the base material that Newton used to devise the theory in the first place. The relation between the sun, the earth, and the moon.
Just fundamentally off from the get-go, huh?
It's poisoned.
Supposed to be
never had a chance.
Supposed to be based off those observations. So he did some math to predict the motion, and guess what? That motion produces different motion than those observations. So what do you?
Right?
What happened?
So you make the masses different, you make the radii different until you get them just right. So the orbit, so the average is just going, and you got yourself a theorem, and then you throw it in the textbooks.
Talk about post-dicting to get it right, man.
That's how it is, boys. And it leaves us with the same conclusion as we came to in part one.
Gravity's a mathematical lie. Yeah,
dude,
perfect.
fantastic breakdown, and the free body diagram at the end there is just icing on the cake. So if anyone's ever like, no, but Newton, and no, it works, like, just look, where's your diagram to show what happens when you add all the forces together? Because when you see the lines go in the other direction, like that's not allowed to happen.
I can refute it right now, Alan.
Like,
ready? You did it wrong.
You go. I got you. Relativity, general theory, bends space time around, all that. So the vector, it looks like it's going that way from your perspective.
It looks like it's wrong. Yeah, it's right.
Yeah, you're just using the wrong tensor, dog. You messed up.
Totally.
So yeah, that's so awesome, Stone. Thank you for that. And that goes. I'm going to play a video to complement the parallel vector diagram that you were showing there, because that's what I just learned about today, coincidentally, and it really just screams like you're not allowed to do that. It has to be inward. So it really solidified the significance of it for me there on that one.
It is my absolute pleasure to deliver the mathematical truth of the Globie assertion. Glom. Swarm. Yeah.
The glom.
Yeah.
All right. So
much fun.
I'll play this out real quick, and then we'll outro. This is a lad explaining Einstein's field equations, and he gives an example here. Oh,
one sec. Just before we go to Einstein, anybody checking the chat? Are there questions or?
Oh yeah. I was reading through. Nobody had any questions thus far.
They're liking it. That's good to know. Okay,
Yeah,
back to
everyone's
Einstein.
chilling.
I heard the globe
Yep.
is getting stoned and then stoned hard. Those are the questions that I heard.
Stone cold glow or something
You
like
gotta
that.
have appreciation for that. Right on.
Is Alan muted? Is Alan talking to us?
The actual feed's muted. So no, we don't hear any audio for
Nothing happened, Alan. I think you're having Linux problems, Alan, to be honest.
that.
Still having them, whatever they
All
are.
right, Shane,
There
new
we go.
strategy. I'm going to send you the link and you play it.
Uh-huh. Do we
All
know?
right, there we go.
Okay.
He's surrendering to Bill.
That's what just happened, but we'll talk about it later.
Yeah. Go to I didn't send you the timestamp, my bad. Hit this one instead. Should take you right to it.
Hello. Today I'm going
Sounded like you were trying to
You
besmirch Linux, and like
direct-
obviously that's not. It's
Only in like a vague
Well,
roundabout way, so I
You make it so easy.
wouldn't worry.
listen. If Linux was here, you wouldn't say that to his face or whatever.
You mean Linus? Yeah, I get you.
Yes, yes. All right. Cool. Yep, that's about it. Back it up like 2 seconds, I think.
Kill that mute.
Yeah.
Oh yeah.
and you keep it oriented in the same way, so it travels
Back it up 10
parallel
more
to
seconds.
itself.
Okay.
The arrow key back one.
Oh.
No, you went hella back.
Yeah, it's a really long video, dude. It's tiny,
Yeah,
minute
yeah.
motions have a big effect. So.
Yeah.
Yeah,
There you
use your
go, you're
arrow
good.
keys
That's
5
it.
seconds
That's
at a
perfect.
All
time.
right.
That's perfect.
A vector, of course, will have magnitude and direction. And what you do is you what's called parallel transport it around the path. That means you keep the same length of vector and you keep it oriented in the same way, so it travels parallel to itself. So all of those lines are intended to be, my drawing may not make it quite so obvious, but they are intended to be the same length, and all of the vectors are parallel, so they just keep parallel to themselves until you get back to where you started. And of course, when you get back to where you started, your vector will be of the same length.
And now
it
you
will be
have
in
a
the same
hairbrush.
direction, because it's always moved parallel to itself, so it will come back to where it started. Okay, all very well and good, but now let's take a cone. Here is a cone which I have made for illustration purposes. As you can see, it's a curved cone. But what I can do is I can cut down the side of the cone and open it up. So if I make a cut along one line, I can then open the cone up and it becomes flat and it has that kind of shape. So let me recreate the cone. I just bring those two lines together. When it's a cone, that edge is joined up. So in a sense, this edge here and this edge here are the same line, the same point on the cone. So let's just draw what the cone looks like when you open it up. You cut down this point here and you
Here comes
open
the
it
tangential
up,
vectors.
and you get a shape that looks like it's a circle but with a slice taken out of it. That's the cone. Just a quick
Make sure
reminder.
the Pac-Man doesn't bite you
There
in
it
the knee.
is, the cone.
Yeah.
And
it is
remember
the
that
Pac-Man.
the line OA and the line OB, when they are in a cone, are the same line. It's that dotted line. Now I'm going to do a bit of parallel transporting, and to remember where the vector was, let me just take that B out of the way and put it there. AB. I'm going to have a vector which continues the line OB. So it's just a straight continuation. And now I'm going to parallel transport that vector around the cone. Remember, it stays the same length, though mine may not. It always stays parallel.
God, he's
We
terrible.
keep going until we get
The artistry.
He's doing his best.
A, and we stop because A is point B. Remember, they are the same points on the cone. But what has happened? Well, the length of the vector is the same, but the direction of the vector has changed. You can tell it's changed direction because I started it as being an extension of the line OB. And OB is the same as the line OA. Remember, it's this dotted line here. So if the vector were to be in the same direction, it should end up like that. But it didn't. It ended up like this. It's gone through an angle. So although the length has remained the same, the direction of the vector has changed. And that is a measure of curvature. If you parallel transport
You could pause.
a vector around.
All right, so slightly different mechanism in the calculation, but the vector parallel thing super on point because that's what it when you complete it, it's supposed to, all be in the same direction. So in Stone's example, it was supposed to be radially inward. Otherwise, it's going to be pulled out. It's going to do the thing that we've all been saying, like, hey, how come it doesn't pull the thing out and ruin everything? And they're like, nah, it just works out. Trust us big formulas. Nah, we just had a guy make the diagrams for the formulas and none of it, they go in the wrong direction.
Well, if
It was the exact thing we've always been saying.
If I'm understanding what he said, what happened is the vector transformed its direction via a magnitude that is that angle. So it went through the whole angle by the time it went around. So it was constantly changing direction the whole time, right? But still. Yes, from the starting point to the original point. So in this relation, this is like for something else for space-time curvature, and then the guy was relating it to a different parallel as well. All right.
For gyroscope measurements. But the notion of the vector change there would be like a measurement of ground curvature or whatever, but that's for a separate thing. But anyway, the relationship was the vector diagram, and then.
Well, I take issue with what he just showed you on that paper. That's the standard mathematical bullshit they always come across when they try to assume vector addition is going to be the same entity between a flat disk like this with a chunk, Pac-Man, and an actual physical cone in 3D space. I mean, the first thing he did was draw a vector coming radially out of a flat disk, and then pretended that it's different. Somehow a different vector when it's not radial on the other side of the Pac-Man's mouth. That is misappropriation.
Oh yeah, see it should be straight. Yeah. Well, he did it as a continuation of the
all of those lines he drew right there should have been radially drawn, not drawn in parallel, until he forms the flat disk here into a cone. They should all appear parallel. Sure.
Yeah.
You know what I mean? Or radial rather. They should all appear radial while we're looking at the flat disk. And when he forms it into a cone, then magically those will all become parallel. But he's not showing that. You know what I mean? It's that is a mathematical misappropriation there.
So they should
be confuse me.
It should be going straight down from the center point, right? Is that what you're saying?
What he's drawing right there, he shouldn't have drawn parallel lines because he's flattened the cone. Yeah, all references to the center have changed.
Yeah, he's drawing
orientation.
I think he's drawing the vector on the actual cone, but depicting it on the circle by side, which is confusing as heck, right? He's doing the
representation. Gotcha. It doesn't go parallel until he cones it.
Yeah.
Gotcha. He did it backwards.
He's swapping you. He's swapping. He interrelates the two of them. There is no relation between the two of them geometrically speaking.
Unlucky, dude. That general relativity will do that to you. Sometimes you just calculate out that curvature and forget you did it backwards.
I think this is how they thin out the audience and only the gullibles remain in the class. You know what I mean? The guys who just shut down their thinking and they memorize what they see and they regurgitate what the teacher wants to hear and you get the grade. But the people who are like myself in this instance, where it's like, no, you just drew an axial vector and then a whole bunch of other parallel lines to it that are meaningless to the significance of the geographical shape that he drew.
Well, devil's advocate. So you think you're smarter than Einstein?
Well, shit, bring him over. Let's chat. Yeah, I don't know, man.
No, that's awesome, dude. Thank you.
I think that'll take us over to my video, a couple thoughts about Einstein shortly enough. And then, yeah, we'll find out. Anyways.
Awesome, dude. Well, thank you so much for the breakdown of heliocentrism, and which is entirely supported by Newtonian dynamics, which had to be later abandoned to introduce space-time curvature, because you can also move straight and in a curved path simultaneously.
Curvilinear.
So long as you just merge the definitions together and tell everyone it's associated with complex maths that they can only understand if their brain was big enough, and if their brain's not big enough, they can't comment on it. So that sucks. So we'll go ahead and outro. And see you guys next week. Karen B, what do you got coming up this week?
Coffee talk tomorrow morning if anybody's around and wants to hang out.
Awesome. A little
Nice.
coffee of the talking.
Mm-hmm.
I think there's also a esoterica.world event coming up. If you guys
Yes.
go to esoterica.world, I'll put the link in the
Yes, there is.
.world.
What are you presenting next week here? Is it you, Alan? What are you presenting next week? No.
I'm not entirely sure, but I think it'll be following up on the stuff with the Japanese model and
celestial sphere.
and
Nice.
then how the Jesuits reintroduced the celestial sphere model to the Chinese, who had already used it 200 years prior to the introduction of the Jesuits to map the entire world, so that they could contextually retell the story as if the Jesuits delivered them the coordinate system that allowed everyone to map the world. So it'll be, dude, it's so crazy what happened. So
Nice. That'll be a good one.
Be something in relation to that, probably. So Cami, if you're there, what do you got coming up?
Oh, I am here. I am going to be in Coffee Talk tomorrow morning, and probably working on the Esoterica conference, and that will give a heads up probably the last week on this pricing as we get closer and tie it into it. We will be like adding in more speakers and changing things out a little bit, but we do have like the early bird pricing going on, and so I do know that that's getting ready to change, I think on the 18th or so. So that is coming up. So I think that's tomorrow.
Awesome.
And
it's going to be awesome.
Other than that, just getting things this summer done and keep on going.
Nice. Stone G, what you got coming up this week, big dog?
I am just a broken record. Life is just, it's going so slow this winter. What can I tell you? Life getting in the way, in real life stuff getting in the way. Still got 2 videos on the front burner. Just gonna pump them out sooner or later. And
nice.
Yeah, that's about where we're at.
Awesome. Looking forward to those releases.
With our temperature here at over 100 degrees real feel, it's just fun to hear that you are in wintertime.
I know. Nice. I see you in there with your sweater on, and I'm like, what?
What are you doing?
I know.
It's everything to stop me from grabbing my neck tube and putting that onto. Like, I take hot over cold any day of the week. Any day. Way
Me
better
too.
than cold. Oh, man.
Mm-hmm.
So enjoy it, guys. It's not going to last.
What do we got going on Tuesday? Someone's doing a prize that on Ether Cause. That'll be awesome.
Ooh. So you know that thing I was talking about?
Oh, you're
the
gonna
Japanese and the Chinese.
You're gonna trial it Tuesday and polish it for Sunday.
Between now and Tuesday, it'll be done. Somehow.
Nice. And what we got Thursday, I think we're doing a Clubhouse thing on Discord, on the Clubhouse Flat Earth Gang Discord. So check that out on Solarium.
Oh, yes.
Right.
Yes. Join the Flat Earth Gang Discord for Thursday. Check that out. And then also Monday will be Celestial Theody update 16, I believe. So we'll be going over update number 16. We just found how to derive the actual refraction that corresponds to the measurement. So we'll be going over that new discovery. And then we'll be going over the, the mysterious half equation that was presented by Jesse last week to, the globe just mysteriously showed up here with no other intervention. So we're going to be going over the trigonometric functions that led to that actual angle there and why it gives the distance that the globe predicts, using air quotes there. All right. So we'll be going over that on Monday, all on 8 p.m.
Nice. Full week.
Full week.
On. Thanks for stopping by, gang.
Yep. See you guys next week.